In this video is part 2 of section 5.5 dealing with the substitution rule. In the last video, I provided a lot of examples on how to use an appropriate use substitution to integrate problems. Now we're going to look at definite integrals here. So now the substitution rule is also needed for definite integrals as well. In fact, there are two ways that you can proceed to do definite integrals here. One is this: you may use the substitution rule to find the antiderivative f as described in a previous video, and then use the fundamental theorem to evaluate f of b minus f of a. Okay, so you can first integrate as we normally did in the previous examples in section 5.5, and then use that fundamental theorem of calculus by doing f of b minus f of a. You can refer to that in section 5.3 when we talked extensively about that. Now, alternatively, this is the second way you can do this. Once you have changed variables from x to u, you may also change the limits of integration and complete the integration with respect to u. Specifically, if u is equal to g of x, then the lower limit, x equals a, will be replaced by u equaling to g of a, and the upper limit, x equals b, will be replaced by u equals g of b. Here, the second option tends to be more efficient, and we can use that whenever possible. So the approach is summarized in the following theorem, which is then applied to several definite integrals. So here's theorem 5.7, and it states, for the substitution rule for definite integrals, let u equal g of x where g prime is continuous on the closed interval a to b, and let f be continuous on the range of g. Then the integral from a to b of f of g of x times g prime of x dx would be this. The integral from g of a to g of b is equal to f of u du. All right, so now let's apply let's apply that theorem to some of these problems here. Starting with example 13, and this is just a continuation of section 5.2. Here we're going to use a change of variable or the table to evaluate the following definite integral. Here we got the integral from 0 to 1 of 6e to the 2x dx. The integral from 0 to 1 of 6e to the 2x dx. And in this case, we'll first start by letting the u be that exponent for the e. Because when we got e to something, it's best to let the u be whatever that exponent is for the e. So I'm going to let u equals to 2x. And then du, of course, will be 2 dx when we take its derivative. Okay, now, let's do this right here. I want to put the 6 out in front, so it'll be 6 times the integral from 0 to 1 of e to the 2x dx. Now I've got dx, so I need to get dx by itself. I'm multiplying it by 2, so let's go ahead and divide both sides of this equation by 2. So here we got 1/2 du is equal to dx. Now, in this case, I'm going to change my limits of integration for u. Now notice that I got x is my lower limit, that's 0, and x is my upper limit is 1. These are for x, and if I want them for u, I have to use this, the fact that u is equal to 2x, and just replace each x with those limits that I have here. So if x is equal to 0, that means u will be equal to 2 times 0, which is 0. And if x is equal to 1, that means u will be equal to 2 times 1. That's going to be equal to 2. So my new limits are going to be from 0 to 2 instead of from 0 to 1. So I'm going to bring over the 6 times the integral of, and I'm going to replace my limits that were for x with these limits for u, 0 to 2, times e to the, now that 2x right here, that's going to be the u. Dx is going to be 1/2 du. So that's going to be e to the u times 1/2 du. Now I got the 6 here, and I'm going to pull the 1/2 in front. So it'll be 6 times 1/2 times the integral of e to the u du. And this is going to be from 0 to 2, so I don't want to leave out those limits of integration. Now, half of 6 is 3, and then the integral of e to the u du, well, that's simple. That's just going to be e to the u. And this will be from 0 to 2. As you see here, I'm not replacing that u with that 2x here, because from 0 to 2, that's going to be in terms of u. Those are my limits for the u right here. And from here, I can go ahead and do the upper limit minus the lower limit. All right, so I have 3 times e to the upper limit, that's 2. I'll tell you what, let me put the e squared in parentheses, minus e to the u, which is my lower limit, that's 0. So I have 3 times according to e squared minus e to the 0 power. And I'll leave this as e squared, but e to the 0 power is 1. And if I distribute the 3 over the e squared minus 1, it would be 3e squared minus 3. And I will go no further than that. Okay. So here we can change our limits of integration here. These limits of integration from 0 to 1 was for x. Then when I change the integration limits from 0 to 2, that's going to be for u. And then just substitute the u with those u limits. Okay, here's another example. All right, let's say I have the integral from 0 to 1 of 2x divided by x squared plus 1 quantity cube dx. Okay, so let's get a u substitution here by letting u be equal to what's in the parentheses there in that denominator, x squared plus 1. And then du will be equal to the derivative of x squared plus 1 would just be 2x dx. Guess what? That's exactly what I have up here, 2x dx. Okay? So I don't need to manipulate this to get something by itself, so I can do the substitution, because that's exactly what I have here. And I'm going to do like I did in that last example, and that would be to change these limits of integration to the ones that's going to be in terms of u. So if I have x equals 0 and x equals 1, starting with x equals 0, I just replace the x with 0 in that u equal x squared plus 1. So it'd be 0 squared plus 1. That ends up being 1. And then for x equals 1, replace this x with 1 in the u equal x squared plus 1. So it'd be 1 squared plus 1. Well, here 1 plus 1 is 2. So my new limits are going to be from 1 to 2. So I have the integral from 1 to 2 of, now that 2 dx, that right there is du. That x squared plus 1 will be what u is. So here's what I'm going to have. The integral from 1 to 2 of du divided by u to the third. And I'm going to pull that u to the third out of the denominator. So I have the integral from 1 to 2 of u to the negative 3 du. And I'll have to use the power rule to integrate this. So that means I increase the power by 1. So that'll be u to the negative 3 plus 1, that's negative 2, divided by negative 2, that's your new exponent. And this will be from 1 to 2. And let me rewrite this as, I'm going to put a 1 in the numerator. The negative 2 stays in the denominator, but that u to the negative 2 will go in the denominator as u to the second. So now you got that from 1 to 2. So now we got the upper limit minus the lower limit here. So this will be 1 over 2 times, actually negative 1 over 2 times 2 squared minus my lower limit, which is going to be negative 1 over 2 times 1 squared. So in this case here, negative 1 over, let's see, 2 squared is 4. 4 times 2 will be 8. Minus a negative, that's going to be a plus. 1 over 1 squared is 1 times 2 is going to be 2. So I got negative 1/8 negative 1/8 plus 1/2. Since I don't have my calculator with me, I can do this. The common denominator for 2 and 8 will be 8. 8 goes into itself 1 time. 1 time negative 1, that's negative 1. 2 goes into 8 4 times. 4 times 1 will be 4. So I got negative 1/8 plus 4/8, which will end up being 3/8. Okay. So sometimes you can see that it's a lot easier to change your limits of integration and then go directly substituting your values for u into that function. Okay. Let's look at problem example 15. Let's say I want to use a change of variables or the table, and I'm going to use the u substitution to evaluate the integral from negative 1 to 1 of x squared times e raised to the x cubed plus 1. Well, I got the e to the x cubed plus 1, so let's use that x cubed plus 1 as u. So I'm going to let u equal x cubed plus 1. Let u equal x cubed plus 1. So that means du would be 3x squared dx. Du is going to be 3x squared dx. And I'm going to rewrite this as the integral from negative 1 to 1 of, I'm going to put the e to the x cubed, then plus 1 in front, and behind it would be x squared dx. So here I need to get x squared dx by itself so I can do the substitution. It's being multiplied by 3, so I need to divide both sides by 3. So that means I'm going to have x squared dx, and that's equal to 1/3 du. And I'm also going to change my limits of integration from negative 1 to 1. So here I got x equals 1 and x equal negative 1. Well, if x is 1, that means 1 cube, and I'll write this out, u is equal to 1 cube plus 1. 1 cube is 1. 1 plus 1 is 2. And then for the negative 1, that'd be u is equal to negative 1 cube plus 1. Cube of negative 1, that's negative 1, plus 1 is 0. So actually, it's going to be from 0 to 2. I just wrote it backwards, but it's the same way. You want to make sure that your lower limit goes with the right one. For the negative 1, that'll be 0 for the u, and the upper limit is 1, they'll be with the 2. So it'll be from 0 to 2. Okay, so I have the integral from 0 to 2. Now that x cubed plus 1, that's your u. The x squared dx, that would be, in this case, 1/3 du. 1/3 du. And I'll show that as is. This will be e to the u times 1/3 du. And I can pull that 1/3 out in front of that integral sign. So it'll be 1/3 times the integral from 0 to 2 of e to the u du. So I have 1/3. The integral of e to the u du, that's the simplest integral, which is, of course, e to the u. And this will be from 0 to 2. So now I'm going to have 1/3 times. I'm just going to focus on just that e to the u by doing the upper limit minus the lower limit. My upper limit is e squared minus the lower limit, that'll be e to the 0. Bring down the 1/3 times the quantity e squared minus e to the 0 is 1. And I will go no further than that. So it will the integral from -1 to 1 of x squared times e to the x cubed plus 1 will be 1/3 times the quantity e squared minus 1. And finally, example 16. Let's say we got the integral from -pi3 to -pi4 of negative sine x divided by the cosine of x, cosine square of x, dx. Now we got a trig function involved here. All right, let's see what we can do with this. That denominator of cosine squared x. What I'll try to do here is write this as the integral from -pi3 to -pi4 of negative sine x divided by, and I'll write this as cosine of x, and that'll be squared. That's just another way of writing cosine square of x. So you can see here, I can let u equal to the cosine of x. And then du, the derivative of the cosine of x would be negative sine x dx, which is exactly what I have here. And I forgot to put dx in. Let me put that there. So here, that's exactly what I have here, negative sine x dx. I'm also going to change my limits of integration here as well. Now, my lower limit is that x is equal to -pi3. Upper limit is x to the -pi4. Okay. -pi4. So if x is -pi3, let's see if we can find the cosine of -pi3. Now, you might need to look at your unit circle for the inverse sine and the inverse cosine. So not the inverse, the inverse circle, okay? Cosine of -pi3 is actually 1/2. And for -pi4, the cosine of -pi4 is actually going to be the square root of 2 over 2. Refer to the unit circle back in section 1.4 for those trig values, for the values of your trigonometric functions here. Okay? So this will be your lower limit. This will be your upper limit from 1/2 to square root of 2 over 2. So I have here the integral of from 1/2 to the square root of 2 over 2. And in this case here, that negative sine dx, negative sine of x dx, that's your du. Cosine of x, that's going to be u. So here I got the integral of du over u squared. And then I got the integral from 1/2 to the square root of 2 over 2. The u squared, I can pull that out of the denominator, right? That is u to the negative 2 du. And I applied the power rule by increasing the power by 1 and dividing it by that new exponent. So this will be u to the negative 2 plus 1 will be negative 1 divided by negative 1. And that's going to be from the square root of 2 over 2. And then as the upper limit, 1/2 would be the lower limit. So it's going to be from 1/2 to square root of 2 over 2. And I can write this in a different way by writing it as a negative in front, 1 over u. That'll be from 1/2 to the square root of 2 over 2. And then do the upper limit minus the lower limit. So here I got negative 1 over, this u will be the square root of 2 over 2 minus negative 1 over my lower limit, 1/2. And let's see how we can simplify this. The reciprocal, and I know it's going to be negative, the reciprocal of the square root of 2 over 2 will be 2 over the square root of 2 minus, let's see, negative, and I might want to put this in parentheses here. The reciprocal of 1/2 will be 2, so I have negative 2 here. All right, now I'm going to do 2, well, actually negative 2 over the square root of 2 off to the side, because I'm going to rationalize that denominator by multiplying the numerator and the denominator by the square root of 2. So I have a negative 2 square root of 2 over the square root of 2 times itself will just be 2. And then this will end up being, if I divide this out, negative square root of 2. So negative 2 over the square root of 2 will just be negative square root of 2. Minus a negative 2 will be plus 2. So it'll be negative square root of 2 plus 2. We can just write that as 2 minus the square root of 2. Okay, and that will be what the integral from negative pi thirds to negative pi fourths of negative sine x divided by the cosine square of x dx will be. Okay, so that does complete this video and this section on section 5.5 dealing with the substitution rule. Feel free to reach out to me if you have any questions about any of the problems that were discussed in this video or any of the homework problems that are in my math lab. So good luck with the homework.